Okay, today we will discuss logic programming. Prolog is one of the widely used logical programming. Taking that as an example, probably we'll try to discuss the programming constructs of the logical programming. This is another different programming methodology, right? The approach is to express the programs in a form of symbolic logic, right? And use a logic inferencing process to produce the results based on certain axioms. Okay, logic programs are declarative rather than procedural, which means that only the specification of the desired results are started rather than detailed procedures for producing them. Programs in logical programming language are a collection of facts and rules. Okay, facts are nothing but the data and the rules, right? Such a program is used by asking it questions, which attempts to answer by consulting the facts and the rules. Consulting here is perhaps misleading. The process is far more complex than that word connotes. This approach is to solve the problems which addresses only a very narrow category of problems. Fine. Programming that use a form of symbolic logic as a programming language is often called the logic programming. And languages based on symbolic logic are called the logic programming languages or declarative languages. The syntax of logic programming language is remarkably different from that of the imperative and functional languages. Like C. Of course, is a structural programming language. At the same time, it is imperative and as well the functional. Pure functional languages like Lisp and probably we'll study in the next unit. Right? The semantics of logic programs bear little resemblance to that of imperative language programs. So we'll first look at the introduction to predicate calculus because it's based on the predicate calculus. So it's a declarative kind rather than a procedural, as I said, right? No, what is a proposition? Proposition can be thought of as a logical statement that may or may not be true. It consists of objects and the relationships among the objects. The formal logic was developed to provide a method for discarding the propositions, with the goal of allowing those formally stated propositions to be checked for validity. The symbolic logic can be used for the three basic needs of formal logic: to express propositions, to express relationships between the propositions, and to describe how new propositions can be inferred from other propositions that are assumed to be true. Basically, the symbolic logic can be used to define three basic needs, right? One of the is the proposition, how to express the propositions and how to express the relationships between the proposition and how to infer the new proposition from the existing one, right? There is a close relationship between the final logic and the mathematics. In fact, much of the mathematics can be thought of a term of logic. The fundamental axioms of number and set theory are the initial set of propositions, which are assumed to be true. Theorems are the additional propositions that can be inferred from the initial set. The particular form of symbolic logic that is used for logic programming is called first-order predicate calculus. But it is a bit imprecise, but we'll usually refer it as the predicate calculus. Of course, in the following subsections, we will probably discuss about the same. The simplest propositions, which are called as atomic propositions, which consists of compound terms. A compound term is one element of a mathematical relation written in a form that has the appearance of mathematical function notations. A mathematical function is a mapping which can be represented either as an expression or as a table or list of tuples. The parts of compound term composed of two parts. One is the functor, another one is the relationship, right? The functor, which is a function symbol that names the relations and an ordered list of parameters, which together represents an element of the relation. A compound term with a single parameter is a one tuple. For example, student here having one tuple. How do you pronounce this? By describing a relationship between them. John is a student, right? Similarly, here you can see, fine, the functor like having about two tuple value here, right? Seth and OSX. Seth likes OSX, right? Nick like Windows. Jim like Linux. Like this, you will, pronounce, fine. Form of propositions. Propositions can be stated in two forms: facts and queries. Okay. Fact is a proposition assumed to be true, which are assumed to be true at initial stage. Query, truth of propositions to be determined. Right. Query is the one of which truthness you are going to determine. So these are the two different forms of proposition generally you find in the logical programming. Compound propositions. Compound propositions have two or more atomic propositions. Propositions are connected by operators. The logical operators, if you see, like negation operator, we represent it as not A. And conjunction symbol you can see here, and A conjunction B, or you can pronounce it as A and B. Disjunction symbol and A disjunction B, or you can pronounce it as A or B. Equivalence symbol, A is equivalent to B. Implication, right? You can pronounce it as A implies B, and this symbol you can pronounce as B implies A. Okay. Generally, this you in mathematics consider it as subset. This you consider as superset, right? So if I have superset between A and B, I say A implies B, right? If it is a subset kind, I am saying B implies A, right? Quantifiers, like universal quantifier and existential quantifier. For all, if you want to define certain or assign some value, you can use for all, and for few, then probably there exists, right? You can use, which is said to be existential quantifier. Then causal forms. Too many ways to state the same thing. When you can combine all of them together in a single statement, right? The causal forms can generally consist of two parts: antecedent and consequent, right? You will have antecedent on the right side, consequent on the left side. Okay. If you have one causal form like this, B1 union B2 union so on up to Bn, right? And then you have an implied symbol, A1 intersection A2 intersection A2 so on up to AM. Fine. How do you pronounce this, or how do you check the, how do we determine the truthness of this particular statement? If A1 and A2 and so on up to AM is true, then either B1 or B2 or Bn up to Bn can be true, right? So this is how you are going to pronounce. It means if all A's are true, then at least one B is going to be true, right? Predicate calculus. A use of proposition is to discover new theorems that can be inferred from known axioms and theorems. As I said, there will be three type of facts that you find in that you're going to describe with the help of symbolic logic. One is the proposition, another one is the relationship between the propositions, and then to derive the new propositions or infer new propositions from the existing one, right? So a use of proposition is to discover new theorems that can be inferred from known axioms and theorems, right? You must be having some axioms and theorems available based on which you're going to discover, new propositions. And resolution is an inference principle that allows inferred propositions to be computed from given proposition. In order to prove that the proposition which are inferred from the existing one are to be true. Unification, finding the values for variables in proposition that allows matching process to succeed. Fine. Like for example, when you have a model, to implement, for example, you have a theoretical concept of car, right? Car will have certain functionalities, certain properties and all. But then, in order to understand, you need a model of the same, right? So, finding the values for variables in proposition that allows the matching process to succeed means in order to make the existing theory to be understood or to be proved to be true, fine. You need a prototype of the same, or you need a mock model, or you need an implementation of the same. Instantiation is nothing but assigning temporary values to variables that allows unification to succeed. If I compare it with object-oriented programming language, fine, it's something like creating an instance and then assigning some temporary values with the help of constructor is what's said to be the instantiation. Or if I say just creating an instance, of an ADT, fine, you can say as a unification. Okay. After instantiating a variable with a value, if matching fails, you may need to backtrack and instantiate with a different value, right? So after you instantiate a variable, you want to, you are going to check with the matching values. If the values with the help of which you are going to match the variables after having been instantiated does not get matched, it means it fails, then probably you take a backtrack. Backtrack is one of the designing technique of the algorithms, right? Which is being here adopted in order to make the theorem proving technique to be made possible, right? Proof of contradiction. When probably let us say you have suggested few things, but then the outcome of the same is exactly reciprocal of it, or certain results which are not coincided with the expected one. The contradiction when happens, right? So these contradictions also you can probably prove, right? How you can prove? By taking the hypothesis first. Hypothesis is a set of pertinent propositions that you think of, that like for example, I'll give you an example of operating system. Even in research, people used to follow this hypothetical proofing of theorems or theory of the research, right? They first assume certain things based on the facts that they have, and then they'll try to prove that what they have thought of it to be true with the facts that they are having at the hand, but then what happens, it may not prove to be sometimes true, or it may prove to be true for certain values, but when they take certain other values, it may not prove to be true. So in that situation, you can probably say that this particular theorem which we thought of proving it for certain values have been proved to be true. But then when you have taken certain other values, it is not being proved, since it does not work for that particular values. Fine. That way you can confine the boundaries also sometimes, or else you may fail entirely sometimes because your theorem may not be proved for all such values that you have rather taken, right, with the assumption that you have started with. So, so here generally you will have a goal, negation of theorem stated as a proposition. So the goal which you try to achieve with the help of the hypothesis that you have thought of it, rather, right, if you are unable to reach the goal at all, then you say your theorem proving is failed. But if you able to prove for certain values, then it is partially proved, and the algorithm or your theory is going to be confined to that respective boundaries, rather, right? So generally, this is one of the technique which being basically adopted in research as well, right? For theorem proving. So theorems are proved by finding an inconsistency sometimes, right? So the theorem proving technique, which is being taken, of course, as the basis for logic programming, when proposition used for resolution. They will be used only for restricted, use. You will find Horn clauses as well. They can have two forms of the same. One is headed Horn clauses, in which you will have single atomic proposition on the left side, fine, and you will have headless, that is empty left side, fine, used to state facts and all. So generally, headless Horn clauses are being used to represent the facts, and headed, clauses are being used to represent the clausal forms, right? To prove the theorems, to prove the facts, to prove the inferred propositions. Most of the propositions can be stated as Horn clauses. Like a Horn clause headed, if you see, it will be in this form, right? Fine. You will have antecedent on the right side, consequent on the left side. So, how are you going to prove? For all A to be true, only then at least one of the B to be true. Fine. So, and here you can have only one B out of this. If you're having multiple, then you must be having or, right? Declarative semantics. There is a simple way to determine the meaning of each statement. It is simpler than the semantic of imperative languages. Programming in logic programming is non-procedural. Okay. Programs do not have state. Now, a result is to be computed, but rather the form of the result. So, here, generally, the program consists of what? Certain set of propositions, right? And the relationships between these propositions, right? And you are trying to infer certain propositions from the existing propositions. Right, for theorem proving, in order to reach the goal state, starting from the initial state, right? Probably if we solve certain problems, we may try to understand how we write the programs, the logic programming. For example, you want to sort a list of elements, okay? How do you write a program to sort a list of elements in logic programming? You can see here with an example. Here we are first describing the characteristics of a sorted list. Here we are not going to define the process of rearranging the list. Just define the characteristics of the sorted list. So how is it is represented? You can see here in the first statement. This statement is the headed Horn clause, right? Fine. So here, how do you interpret this? How do you read it? If see, permute is the relationship, and there are two tuples here: old list and new list. So how do you pronounce this? Old list is permuted to new list, right? And this is said to be and conjunction, and sorted, and new list is sorted. First, what is that you are doing? The old list is permuted. It means you have applied the permutations on old list to generate the new list, and the generated new list is sorted. Okay, then you say the old list is, sorted as a new list, right? Old list is sorted as a new list, right? So this is how you will pronounce it. So the procedure now you can see for this sorted. This is a sorted operation that you are performing, right? So this sorted operation we have defined in the subsequent statement, where you can see here sorted list. Here you have implied symbol. So how do you pronounce this? If for all j such that 1 less than or equal to j less than n, list of j is less than or equal to list of j plus 1. It means the predecessor is list of j and list of j plus 1. List of j is the predecessor of list of j plus 1. The predecessor is less than the successor. Okay, for all such j, where j is varying between 1 to n, you say that the elements of list being indexed with this j are ordered in such a way that where the predecessor is the successor, the predecessor is the less than or equal to the successor. Then you say the list is sorted. Got it? Then you say the list is sorted. So this is how you have defined the operation of the sorting on a list, right? And this one you have used here in the above statement. So in the above statement, you have said that the old list is permuted as a new list, and that new list is sorted. Then the old list is generated. Old list is sorted as a new list, right? Okay, this is how you are going to pronounce. The origins of Prolog, if you see, they have actually been invented by certain innovators. Like AX Marcelli, university people who have invented natural language processing, and Edinburgh University people who have probably started this automated theorem proving, have given a way or a path to start or driven towards the Prolog, right? So here, if you look at the different terminology that you are going to use as part of the logical programming, you find term, you find constant, atom, right? Term is a constant or a variable or a structure. Constant is an atom or an integer. Atom is a symbolic value of Prolog. Atom consists of either a string of letters, digits, and underscores beginning with the lowercase letters, a string of printable ASCII characters delimited by an apostrophe. A variable is any string of letters, digits, and underscores beginning with an uppercase letter. Instantiation is the binding of variable to a value, right? Which lasts only as long as it takes to satisfy one complete goal. The structure represents the atomic proposition. Fine. Like for example, functor structure. So you will be mentioning the functor, We generally represent the relationship, of course, between the tuples that you have passed as its parameter list, right? So functor followed by the parameter list, right? So this parameter list can have one tuple, two tuple, or for example, how are you going to represent certain propositions, fine, and describing the relationship between the propositions, fine. We can see with the help of certain facts here available, which are used for hypothesis, and these functors propositions are even said to be the headless horn clauses as well, because you have only the left side, you don't have the right side. Okay, you don't have the antecedents, right? So how do you pronounce this? Shelley is a female, right? See here, this is the functor and this is the tuple, right? So as I said, you will have basically two programming concepts: facts and rules, right? What are the programming constructs as part of the programming logic programming language are facts and the rules, right? So how we are going to define the fact? Based on certain propositions, predicate calculus as we discussed, right? So proposition is basically describing certain relationships, right, between certain entities, right? So here, how do you pronounce this male functor? We say Bill is a male, right? So we say Bill is the father of Jake, right? This is how you're going to pronounce by describing the relationship between the tuples. Right. Now coming to rules. Rules are going to be set, fine, in order to prove the theorems. Fine. You start with the hypothesis. You will have headed horn clauses. The headed horn clauses will have right side and left side. The right side we call it as antecedent, that is nothing but the if part. It could be sometimes single term or it could be conjunction of more than one. And left side you will have the consequent, which is said to be the then part. Must be a single term here, right? Or it can be conjunction, or it could be disjunction, right? So conjunction is a multiple term separated by logical and operations. Like here, look at certain rules defined. See, this is the implied symbol here being used. So you have antecedent functor defined as mother. Parameter list is Mary and Shelley, right? So how do you now pronounce this and how do you describe the relationship between this, couple? Mary is the mother of Shelley, okay? Mary is the mother of Shelley. So here, since this is the antecedent, you pronounce it as if part rather, right? So what do you say now? If Mary is mother of Shelley, then you say that Mary is the ancestor of Shelley. Got it? So this is how you generally pronounce the rules which you are going to set with the help of the horn clauses. It can use the variables. Universal objects also can be used to generalize the meaning. There are certain few more rules have been defined. You can see here. The next one. Yes. So how do you pronounce this? Any one of you from the class?
If X is mother of Y, then
yes.
X is parent of Y.
Yes. Fine. If X is mother of Y, then X is parent of Y. Okay. So similarly, the next one, other form, if x is the father of y, then x is the parent of y. Now, here look at in this rule, you can find there are two propositions, right? Two relationships you have, two functors you have on the antecedent part, right? So in the antecedent, you find here two functors. So how do you interpret this? If
X is parent of Y.
and here what you should say, and y is parent of z, then what you say? Then x is the grandparent of
Z, sir.
Z.
z. Okay, so this is how you're going to pronounce, right? So the antecedent part will have one or more than one functors. Basically, if you have more than one, then you have to apply the conjunction, right? There must be conjunction relationship between them. So you should pronounce it as and there, right? So on the left hand side, you will have a single functor, right? So here, how are you going to pronounce it? If x is a parent of y and y is the parent of z, then we are going to say that x is the grandparent of z. Okay. Similarly, any one of you from your class, the next one, next class.
So if M is mother of X and M is mother of Y and F is father of X and F is father of Y, then X is sibling of Y.
Yes. So this is how we are going to pronounce, right? So in logical programming, you will find only two things, right? You will find facts and you find the rules. Facts are assumed to be true, right? They are generally, what do you call headless clauses? You can say headless on clauses, right? Where you don't have, the antecedent. You will have only the consequent. And rules. Another thing that you have in the logical programming is the rule. A rule is generally represented with the help of clausal form, headed clausal form, right? Headed clausal form will have two things, right? Antecedent and consequent, right? So how do you pronounce? You give if prefix to antecedent, then prefix to consequent. So you pronounce it as if antecedent, then consequent. So the logical programming, if you see, it's all about theorem proving, right? It's all about theorem proving. And you start with some hypothesis. Hypothesis is also some kind of assumed, facts, right? With assumed facts. Then you will try to prove certain goal, right? By setting up some rules. So the rules which you are going to, use in order to prove the goal, fine, is what the theorem proving, that you're going to do it as part of the logical programming. So in logical programming, what is that you do is you will first start with some assumed facts, fine, which are found to be true, which are assumed to be true. So taking these facts as an initial stage, fine, then you use certain rules, right, in order to reach the goal node, in order to prove the theorem, right? So there are two things that you find are facts and rules as part of the logical programming. Facts are the headless on clauses, you can say, and rules are the headed. Fine, that's it, right? This is all about the logical programming. We can see most of our theorem proving in the logical programming taking only these two things into consideration. Fine. goal statement. For theorem proving, theorem is in form of proposition that we want our system to prove or disprove. So the rules which you probably consider to reach the goal node, you may sometimes able to prove it or maybe disprove it, as I said, because the hypothesis is nothing but the assumed fact that you have taken. Fine. That may lead to truthness of the theorem, or sometimes it may disprove it also. Fine. So taking all possible situations and the rules into consideration based on those hypothesis, you try to achieve the goal node, right? If you are unable to reach the goal node, you say it is disproved, right? These are the headless horn classes said, and this is the conjunctive propositions and proposition with variable also legal here, like how Fred is a man, right? X is father of mine. Inferencing process of Prolog, right? Inferencing generally you are trying to generate a new proposition from the existing proposition is what should be the inferencing rather, right? So see the query which you are given, you are asked to prove is what said to be the goal, right? Queries are nothing but the goals rather, right? You want to reach that particular goal, right? You are asked to solve the query. The query given to you to solve rather, right, is nothing but to prove whether that you can rather reach with the facts that you have at your hand. Fine. So with the rules that you can probably apply to the facts and try to reach that goal or answer that query, right, is what basically the inferencing process of Prolog is, right? If a goal is compound proposition, each of the fact is a sub-goal. To prove a goal is true, must find a chain of inference rules and of facts. For goal Q, let us say certain facts given below, and you are asked to prove Q to be true, right? So how do we do this? Now, when from where to start and how we can probably reach it, rather, right? So in order to say that Q to be true based on certain facts that are given to you, fine. Is what the inferencing process is, right? Is what the theorem proving, right? Process of proving a sub-goal called matching, satisfying, or resolution, right? There are two different approaches generally you find here while you are trying to resolve the goals or queries. One is bottom-up approach, which is said to be the forward chaining, and another one is the top-down resolution, or the backward chaining, right? The bottom-up approach begins with facts and rules of the database and attempts to find the sequence that leads to goal. Works well with a large set of possibly correct answers. And top-down resolution or backward chaining, if you see, it begins with goal and attempts to find sequence that leads to set of facts in the database. So top-down is like going in a reverse manner. You start with a goal, right? Instead of with facts, you start with a goal and attempts to find the sequence that leads to a set of facts in the database. Trying to find the facts which are available in the database to be true. Starting with a goal. Works well with a small set of possibly correct answers, right? Prolog implements use backward chaining. If you use the backward chaining here, of course, these are the two different approaches that most of the programming, logical programming languages that adopts, but Prolog is making use of what? The backward chaining, right? The sub-goal strategy. When goal has more than one sub-goal, can use either depth first search, find a complete proof for the first sub-goal before working on others, or breadth first search, work on all sub-goals in parallel, right? But here Prolog uses the first search. I hope in data structure you may have studied this depth first search and depth first search. In breadth first search, you will try to explore all the child nodes of a node before you reach the goal node, right? Only after exploring all the nodes, you can probably reach the live node. But in depth first search, what you do, you will explore only, the node only the live node rather, right? And you will reach until the leaf node once in that particular path, and then you will take a backtrack to solve the or to reach the goal node with alternate rather, right? Taking another live node, right? So that's what exactly the depth first. In depth first search, what happens? Backtracking will take place, right? I'll give you an example here. In breadth first search, for example, you have one node. You have child node like B, C, D, E. Okay. Then you have, let us say, F, G. Here you have, let us say, H, I, J, K, L, and M. Let us say you have like. So in breadth first search, how do you go? You go breadth-wise. I mean, you will explore the root node. When you explore the root node, you find all the child nodes to be live nodes. So all these live nodes are going to be explored, right? It means D will be explored, and C will be explored, D will be explored, E will also be explored, right? Then you will go like this, right? Okay, this is the breadth first search. But in depth first search, what happens? The same you have, fine. You will explore only the live node, right? Until you reach the goal node. If you could not able to reach in that particular path, then you take an alternate, right? By taking a backtrack. Like for example, you start with the root node A. When you explore, you get all these nodes, but this becomes your live node here, and you will explore only this. When you explore this, you get E and F, right? Then you will explore this, right? It means you will first reach like this, fine. This entire path will be finished in order to see that whether E is your goal node, because until you reach the leaf node, you will be trying to traverse, fine, and you are trying to solve it rather, right? So once you reach the leaf node, right, generally your goal node will be at the leaf node only, fine. So until you reach the leaf node, you will explore it, and you will then ensure that it is not your goal node. Then you take a backtrack, right? You come to the backtrack. When you come, it means you go a step back. When you go to a step back of it, what is the alternate path? This is the alternate path. So you will traverse this. It means you see that whether F is a goal node. Even if F is not a goal node, then you take a backtrack. You step back. When you come here again at A. So what is the alternate to the previous one or the existing one? Is obviously C, right? So then you try to explore this. When you explore this, you will get this. So you will then reach this, right? You come like this, fine. If you could not reach here, then you take a backtrack here. You traverse this, and you could not find. You come, you go a step ahead, and then take an alternate path. So this is the alternate path. Then like this, okay? Then like this. Then like this. It means you go like this, fine. You can see you first explore until you reach the leaf node in order to ensure that you may be able to reach the goal node. If you could not able to reach, then you take a back step down, backtrack, and then you will then explore it, right? That way you can probably try to reach the goal node. But in BFS, what happens? You will when explore the root node, you get all these live nodes. So all these live nodes are going to be explored. Fine. Before you reach the goal node or you reach the leaf node, right? You will explore all this. Then you will explore this nodes. Two nodes, and this particular child subchild, this particular child subchild, like this. So you will be going breadth-wise. So in this, what happens? The number of nodes that you are going to traverse is more rather. You are going to, if say for example, your goal is somewhere here or somewhere here also. If your goal is somewhere here, or your goal node is somewhere here, let us say. Even if your goal node is somewhere here, you need to explore all the nodes, right? But in DFS, you can see when the goal node is somewhere here, you will be able to explore only these nodes. It means you are you are being rescued from exploring all this. It means you are able to rescue a lot of time, right, from exploring this. Then obviously the efficiency is better, right? So that's how DFS is better. So these are the two approaches which can be rather adopted, but you can see here Prolog is adopting the DFS approach, since DFS approach is more efficient than compared to BFS, right? So that's what, as I have discussed, backtracking is the approach which is being here adopted, in order to reach the goal when it, eventually first reach with certain facts to the goal node by exploring certain live nodes starting from root. But once it could not find it certain, goal node with the exploration of certain live nodes, then it take a backstop and a backtrack, you can say, and then it look for the alternate path, and in that alternate path again it tries to then resolve its query to reach the goal node. If not, then probably take another back step, backtrack, and find the alternate path of the same, and then try to resolve the goal node in that particular alternate path. That way, it eventually resolve the query in order to ensure that the goal will be reached.